The night sky appears calm and peaceful to our eyes. We look up and see the familiar comfort of stars, like tiny pinpricks of light scattered across a vast, dark canvas. We see the steady glow of the moon, our constant companion, and the bright, wandering planets. But this serene picture hides something profoundly strange and powerful. The silent darkness between the stars conceals some of the greatest mysteries in the entire universe. It hides the quiet, lurking presence of black holes. These objects are not just cosmic curiosities, they are fundamental forces of nature. They are quiet, but they are unimaginably potent. They challenge our deepest understanding of space, time, and reality itself. A black hole is, in its simplest form, a place in space where gravity is overwhelmingly strong. Imagine a pull so intense that nothing, not even the fastest thing in the universe, can break free from its grasp. That fastest thing is light. To understand a black hole, we must first understand its most defining feature, the event horizon. Think of the event horizon not as a physical surface you could touch, but as an invisible boundary, a point of no return. It is an imaginary line drawn in space around the black hole. If you are outside this line, you still have a chance. With enough power, you could fly away and escape the black hole's gravitational pull. But the moment you cross the event horizon, your fate is sealed. You can never come back out. Not even light, traveling at its incredible speed, can escape from inside this boundary. The event horizon is the ultimate one-way street in the universe. Let's imagine this with a simple example. Picture a powerful waterfall. Far upstream, the current is gentle. You can paddle away from the edge. Closer in, the current grows faster. Cross an invisible line and no effort can stop you from going over. The event horizon is like that line, not a wall, but the point where escape becomes impossible. Black holes are not born from nothing. They are the dramatic final chapter in the life of the most massive stars in the universe. Stars are like giant celestial furnaces. For billions of years they burn through their fuel, creating energy through nuclear fusion in their cores. This outward push of energy perfectly balances the inward crush of their own immense gravity. But this fuel is not infinite. When a truly massive star runs out of fuel, the balance shatters. Gravity wins. The core collapses in a fraction of a second. That collapse triggers a supernova. For a few weeks, one supernova can outshine its entire galaxy. The explosion seeds the cosmos with heavy elements that will one day form new stars, planets, perhaps even life. While the outer layers fly outward, the core collapses inward. Not every star becomes a black hole. Only true giants, 20 to 30 times the mass of the sun, have the gravity to finish the job. For these behemoths, collapse is unstoppable. Gravity crushes matter past known limits into an incredibly small space. Space and time are warped and effectively torn, creating a region nothing can escape. A new black hole is born. A silent monument to the violent death of a once mighty star. A dark, powerful ghost. From shining star to dark singularity. One of nature's most extreme transformations. Just as stars and planets come in many different sizes, so do black holes. Astronomers group them by mass into main types. Stellar mass black holes form from the explosions of massive stars. Typical masses are a few to a few dozen suns, compressed into a sphere only a few miles across. Extreme density. Supermassive black holes are truly titanic. They weigh millions, even billions, suns. Nearly every large galaxy hosts one. The Milky Way's is Sagittarius A star, about 4 million suns in mass. Its event horizon would fit inside Mercury's orbit. We can't see it directly, but we can see stars whipping around it. How did they form? They're too big for one star. Perhaps they started small and grew over billions of years. They feast on gas and dust and merge with other black holes, building monsters over cosmic time. In between may lie intermediate mass black holes. Long theorized, now with promising candidates. Section 5. How we find the invisible. Since black holes themselves are completely dark, finding them requires a clever and indirect approach. We cannot point a telescope at one and see it. Instead, we look for their powerful influence on nearby stars and gas. If you see a star orbiting something that isn't there, circling an empty point at high speed, a massive, invisible object is responsible. By measuring an orbit's shape, speed, and period, astronomers calculate the mass of what it's orbiting. If that mass is huge and tightly confined, a black hole is the only explanation. This is how we confirmed Sagittarius A star at our galaxy's core. For decades, astronomers tracked stars near the center, watching tight, fast orbits around a dark point. The data revealed a compact mass of about 4 million suns. Another method: look for intense radiation from matter falling in. While the black hole is dark, the spiraling material heats to millions of degrees and shines in X-rays. Our X-ray telescopes can spot these beacons across the galaxy. One of the first was Cygnus X1, a massive blue star orbiting an unseen X-ray bright companion too compact to be anything but a black hole. Discoveries like this moved black holes from theory into observational reality. Black holes do more than pull matter in. They fundamentally alter the fabric of reality around them. According to Albert Einstein's theory of general relativity, gravity is not a traditional force, but a curvature of spacetime caused by mass and energy. Think of spacetime as a stretchy sheet. Place a heavy object on it, the sheet curves, guiding motion. A black hole creates a deep, steep well from which nothing can escape. One bizarre effect is gravitational time dilation. The stronger the gravity, the slower time passes. From far away, someone falling toward a black hole appears to slow, their clock ticking ever more slowly. But to the falling person, their own clock is normal. They cross the horizon in finite time. Time is not absolute. It depends on the observer and gravity's strength. Gravity also bends light, creating gravitational lensing, multiple images, arcs, even Einstein rings. These distortions help us detect and weigh invisible masses, including black holes. Sometimes black holes exist in pairs, locked in a gravitational dance. They orbit a common center of mass. Some form from two massive stars born together. Others capture one another later. Over millions of years, their orbit slowly shrinks. They radiate energy as invisible ripples in space-time. Gravitational waves, predicted by Einstein, like ripples from a stone dropped in a pond. As they spiral inward, they move faster and faster, then merge in a burst of wave energy. To hear this faint song, scientists built interferometers like LIGO. Lasers bounce between mirrors kilometers apart, measuring tiny distance changes. On September 14, 2015, they succeeded. The first direct detection from a black hole merger. A faint chirp, perfectly matching predictions from over 1 billion years ago. Since then, dozens more events have revealed how common these mergers are and allowed precise tests of Einstein's theory. The idea of a black hole can be frightening. Popular culture paints them as ravenous monsters, roaming the galaxy, swallowing planets and stars. That image is not accurate. Black holes follow the same gravity laws as everything else. They have no special sucking power. From a safe distance, a black hole is no more dangerous than a star of the same mass. Imagine the sun instantly replaced by a black hole of equal mass. Earth would keep the same orbit. We'd lose light and heat and freeze, but gravity at our distance would be unchanged. The real danger is up close, tidal forces. Gravity differs so much from feet to head that you'd be stretched. Spaghettification. And while nothing escapes from inside, material outside can glow fiercely in the accretion disk. Magnetic fields can launch jets that shine across the spectrum. These beams can travel thousands of light years at near light speed. Black holes are more than just cosmic objects. They are laboratories for the most extreme physics in the universe. They push our best theories to their breaking points and expose the limits of our knowledge. Once a strange prediction on paper, now we have a growing arsenal to study them. In 2019, the Event Horizon Telescope revealed a glowing ring around a dark void, a black hole's shadow. A profound visual confirmation, a century in the making. Black holes sit at the crossroads of general relativity and quantum mechanics. Stephen Hawking predicted faint quantum glow, Hawking radiation, implying black holes can slowly evaporate. Over unimaginable timescales, they can disappear. But what happens to the information of what fell in? This paradox remains unsolved. Black holes are architects of the cosmos, shaping galaxies with energy and jets. By studying them, We test gravity, space, and time beyond earthly limits. The universe is more than meets the eye. Black holes remind us of that truth. The ultimate takeaway: black holes are where gravity wins, and in studying them, we all win a clearer picture of our incredible universe.